So in this tutorial we're going to be talking about fission and how it relates to fusion. We're going to be discussing fusion in the next video, but it's worth bearing in mind throughout the whole thing that fission and fusion are different processes, and eventually you want to be able to describe both of them, but in this one you'll be able to describe fission. You need to know what a chain reaction is and what the control rods do in a nuclear reactor, and we need to constantly bear in mind that with both fission and fusion they are releasing energy. Both of these processes release energy. So if we just take a moment to compare fission and fusion before we get started onto the details of fission. We've said just now that both fission and fusion release energy from the nucleus of an atom. And obviously energy is really useful, there's loads of things we can do with it. And this is why we're interested in both of these processes. Now currently fission happens in power stations and fusion happens in stars. But we are trying to get to a point where fusion could happen in a power station as well. And we're going to talk about why we want to do that in the fusion video. But at the moment fission takes place in power stations, so if there's a nuclear power station it's fission taking place, and fusion takes place in stars out in galaxies and space. Now fission is where you have a large unstable nucleus and you split it into two smaller pieces, whereas fusion is you have two small nuclei and you fuse it together to form a bigger nuclei. So let's look at fission in more detail now. Fission is the splitting of a large unstable nucleus. There are two nuclei that we normally use in fission, plutonium or uranium. And as you can see from the diagram, what happens is we have a neutron here, and that travels towards either a uranium or plutonium atom here. This is the nuclei of that atom being represented. That atom then splits into two smaller pieces, so this piece, and these are known as daughter nuclides. So these are two smaller atoms, and then we have other things given off as well, so some energy, some neutrons, and a bit of gamma radiation. So things that are important to remember: fission is not a spontaneous or random process. Spontaneous fission rarely occurs. Usually for fission to occur the nucleus must first absorb a neutron. Now this is a really important point, because one of the biggest mistakes or misconceptions within the nuclear physics topic at GCSE is to confuse fission with radioactive decay. So previously we were talking about alpha, beta and gamma decay, and we said that an unstable nucleus decaying was a random process and a spontaneous process. It just happens, we can't predict when it happens. But fission isn't like that. We make fission happen because we control the neutrons that go into the atom. So this is different from radioactive decay. Spontaneous fission rarely occurs. Usually for fission to occur, the nucleus must first absorb a neutron that we have provided. So when this neutron is absorbed by this uranium or plutonium nucleus, lots of things happen. This nucleus then splits into two smaller bits called daughter nuclides. There's some gamma radiation given off, there's energy released, and more neutrons, either 2 or 3 neutrons depending on whether it's uranium or plutonium, are released. Really important to remember this energy release, because we use this energy to generate electricity in a nuclear power station. Now we've already looked at nuclear decay equations, and we can use those skills to balance an equation for fission taking place with uranium. So why don't you press the pause button, have a little look at this, and everywhere where you've got a question mark you need to fill in the missing number. So first of all, really important point to just make a note of, these are the products of fission, and they all have kinetic energy after fission has taken place. That's the energy that something has when it's moving. Now these neutrons that are released during fission can go on and be absorbed by another uranium or plutonium nucleus, and those atoms will then undergo fission and they will release another 2 or 3 neutrons, and these can be absorbed by more uranium or plutonium nuclei, and it carries on and carries on. Now the name that we give to this carrying on process is a chain reaction, and this is quite an important thing. So the neutrons can go on to start chain reactions, but if we're in a nuclear power plant, we want to control this chain reaction, because if it carries on without us being in control of it, more and more energy is going to be released, and if we don't control it, we will get an explosion. And that's actually what happens in a nuclear weapon. It's a fission reaction that's uncontrolled. There's an uncontrolled chain reaction, and the energy released is the energy released by the nuclear weapon. But what we need to be able to do is draw and understand diagrams that show a chain reaction. So we're going to draw one now together. So we have a neutron that goes into a uranium or a plutonium atom. I'll just put U there for uranium. That's then going to split into 2 smaller daughter nuclides, and it's going to give out 2 neutrons. Now we've said that those neutrons can then take place in further reactions, so I've then got to draw that again. So this neutron is going to hit this uranium atom, and this neutron is going to hit this uranium atom, and they're then going to split into 2 daughter nuclides, so one there and one there, and then one there and one there, and they're then going to release another 2 neutrons, and this one will release another 2 neutrons. So you can see after 2 rounds of fission, from putting 1 neutron in here, we get 4 neutrons out. And this is why we get so much energy released if we don't control the situation. But I'm then going to show what happens if we do another round of fission. So this neutron will be absorbed by this uranium atom, this one will be absorbed by this uranium atom, this one can be absorbed by this one, and this one can be absorbed by this one. And then they're all going to turn into 2 daughter nuclides. Let's mark those in here. So 1, 2 for that first one, 1, 2 for the second one, 1, 2, and 1, 2. So those are all my daughter nuclides. And then I get neutrons being released again. So I've got 1, 2 neutrons here. 1, 2 neutrons there. 1, 2 neutrons there. And 1, 2 neutrons there. So from having put in 1 neutron, after 3 rounds of fission, I've got 8 neutrons out. So you can see we've got to do something to control this chain reaction, otherwise things are going to get out of hand quite quickly. So in a nuclear reactor, in a nuclear power station, we don't want the chain reaction to carry on and lead to an explosion. That would be a bad thing, because we want to use the energy released to generate electricity instead. So in a nuclear power station, we've got all these different sections, and we're going to talk about what different parts do and how they control the chain reaction. So here we've got the nuclear reactor. This is where the uranium and the fission takes place. Here we've got a heat exchanger. This is where energy coming from the nuclear reactor turns water in this pipe into steam. The steam then goes over these turbine wheels and makes them spin around, and that's then connected by an axle to the generator, which we're going to learn more about next year. And the generator then turns this kinetic energy into electrical energy, which then goes off via the national grid, which we've already learnt about. So let's look at the nuclear reactor in more detail and how that works to make sure that the fission reaction taking place is controlled. So here's a close-up of the nuclear reactor that we saw on the previous page. Now we've got lots of different things here. So what's really important is that we control the chain reaction in a reactor so that we can control the amount of energy being released. Now the fusion is taking place in these fuel rods here, and that's where the uranium or the plutonium is. So that's where the fission is taking place. And the neutrons come out of the fuel rods and they travel over to another fuel rod where then more fission can take place. But what we do to control the chain reaction is we put these control rods, we lower them in between, into this gap here, in between the fuel rods. The control rods are made of boron and they absorb neutrons, so they can't take place in any other fission reaction. So that's how we control the chain reaction. And you can see that the energy released from the fission here in the fuel rods then heats up this liquid or gas, and it travels out of this pipe where the heat is exchanged to this separate water system here, and then this liquid or gas has got cooler and then goes back in, and then this steam, once it's gone over the turbines, will cool and go back round. Really important that we keep these two sets of liquid and gas separate, because this liquid or gas is contaminated. If that escapes and somebody drinks it or breathes it in, they are going to be contaminated. This set of water or gas doesn't have to be contaminated because we've got it separate, so that makes it a bit easier to process all of the waste. Now, one of the really big problems with a nuclear reactor that uses fission is that once the uranium has taken place in a fission reaction and you have your daughter nuclides left, these fuel rods are what's known as nuclear waste. They have a long half-life. They're undergoing nuclear decay and they're very dangerous, and we need to store them somewhere, for between hundreds to thousands of years, somewhere very safe where nobody can get at them or use them, and where they can't contaminate any water or food supplies. So that's a big problem and challenge with nuclear fission reactors, which is why we're trying to develop nuclear fusion reactors, which we'll talk about in the next video. So hope that's been helpful. Write up your summary notes and bring any questions you have to the next lesson.